All right, Mr. Ahmed here for 2.5, and this is going to transition us from the algebra proofs into some actual geometric proofs. And before we actually go into the proofs, what I'm going to take here is some examples of a given that you are probably going to see, and we are going to write what we know based off of the given. When we work on proofs, I always teach the philosophy of once you have a given, use it. A lot of the times I prefer to write my reasons in if-then form. However, it's oftentimes just referred to as the definition of something or a theorem, etc. So what we're going to do is just take the given and then mark what we know in the diagram and then write the next statement as it would appear in a proof. This is just some practice. So if I'm told that B is the midpoint of AC, I know that if I have a midpoint, then I have two equal parts because something is cut in half. So in my diagram, I'm going to mark the congruent segments. And then I'm going to state what I know. I know that AB is congruent to BC. And the reason behind that is technically the definition of midpoint. I'll abbreviate midpoint MP. In if-then form, I would probably say if midpoint, then two congruent segments are formed. That's just kind of nice and short, but I always want to think of the if this was the case, then what do I know? All right. The next one says angle 1 and angle 2 are complementary. So in this diagram, there's a couple things we could piece out of that. I would know that if they're complementary, they add up to 90. So that's what I'm going to write. Measure angle 1 plus measure angle 2 equals 90. Reason, definition of complementary angles. And I'll abbreviate that a little bit with an angle sign. It's a definition of complementary angles. If-then form would be if complementary, then sum is 90. So I'm going to write out the equation. Okay? Angle 1 and angle 2 have to add up to 90 because they are complementary. All right, the next one. This is a big one. And this diagram's not fully drawn for a purpose. It says ray AB bisects angle CAD. So that key word, bisects, coming up again. If an angle is bisected, it's cut in half. So I need to actually take this information and draw it out in the picture. The whole angle is CAD, and A to B is what is bisecting it. So that means these two little angles are congruent. If it's cut in half, they have to be equal. So I'm going to list the two congruent angles. Angle CAB is congruent to angle BAD. Reason, definition of angle bisector. Or in if-then form, I would say if angle is bisected. Oh, I forgot. Oh, I'm going to start that over. If angle is bisected, then two congruent angles are formed. So that would be if-then form. Okay. Typically for the textbook, we're going to use these definitions, but I always like thinking of the if-then because the given leads me to something else I know. All right. Next one says angle 2 is a right angle. So if I'm given a right angle, then I know measure angle 2 equals 90 degrees. Reason, definition of right angle. Or I could also just say if right angle, then 90 degrees. And the last one, 3 and 4 vertical angles. Well, that means angle 3 is congruent to angle 4. And I always just say vertical angles are congruent. This one's probably also referred to as the vertical angles postulate / theorem. Sometimes, actually, it has to be theorem. Not going to be postulate. Vertical angles theorem, because we would have to prove that they are congruent. So it'd be the vertical angles theorem. Okay, so that's just some practice on taking a given and moving on. This one would probably be noticed in a diagram more than it would be written out. So what a geometric proof actually looks like. So the proof is that logical argument that uses deductive reasoning, hence facts, to show that a statement is true. There are several forms of proofs. Typically, we are going to use that two-column proof, just like we did with the algebra statements. The statement's on the left, reason's on the right. We will number each statement in order with its reason also numbered. Oftentimes, people start forgetting to write these numbers down. We do need to number them, okay? So, the first proof. A lot of ours are going to start fill in the blank, okay? We're going to keep these about as simple as possible. And we're going to look at diagrams to set up equations, and once we can set up an equation, it's going to lead us to what we need to end with. What we end with is the statement we are proving. This is exactly what the last statement should say. The last reason should never say proof, proven, proof. Bad. It is an actual property for the last reason. So, usually we'll start with our given, and then from there we're going to have to look at the picture to see what else we can find out. We're going to use angle addition postulates, segment addition postulates, bisectors, things like that. So, first one says, given, angle 1 is equal to angle 3. Notice it is marked, they are equal, they are congruent, so that's what I start with. Measure angle 1 equals measure angle 3. Reason, given, they told me that. Step 2 says we're going to use the angle addition postulate. And it says measure of angle DBA. So, for this problem, I am going to highlight angle DBA so we can see what it consists of. So, DBA, our D isn't actually showing up very well, so I am going to add it in. The D is right here, and our E is right here. Those were super hard to see. So, DBA, highlighted in orange, D to B to A, I traced it. That is equal to angle 3 plus angle 2. Alrighty. Next step says the measure of DBA, so we didn't change anything, is equal to angle 1 plus angle 2. Well, why did I know that was true? Well, 1 and 3 were equal, so I could substitute in 1 for 3. We substituted it in. Next step says measure of angle EBC. So I'm going to identify EBC in the diagram to see what it is that we are looking at with EBC. So EBC is going to get highlighted in yellow. So E to B to C. Now when I kind of look at this, I see I have my orange angle and I have my yellow one. They both share angle 2. 1 and 3 are the same amount. So I mean, some of this is kind of obvious in nature that these have to be equal, but we're just going to take a look and see exactly how we show that they are equal. And the reason that this occurs is 1 and 2. 1 plus 2 equals the whole thing. We use the angle addition postulate. We added the two parts to get the whole thing. And finally, it says we're going to use the transitive property. Well, let's see our transitive property. 1 plus 2, 1 plus 2. Those are the same. They match. So we can use the transitive property to state that the measure of angle DBA is indeed equal to the measure of angle EBC. Notice these two were the same. 1 plus 2, 1 plus 2. Go across, transitive property, ended with exactly what we were proving. Notice the last reason does not say proof or proven. So that's our first proof. All right, next one. Like we said, kind of a fill in the blank type thing. Make sure you're actually trying to step through this piece by piece to see what you're ending at. Don't just look at this and try and find the reason and just assume it's a fill in the blank type question. We have to kind of step through where these other pieces are coming from, even if they're filled in, trying to understand how the whole proof is formed, okay? So, first one says, T is the midpoint of SU, prove that X is equal to 5. So this is what I need to end with. This will be my last statement. Notice that it is. That's where we're ending. So, given says T is the midpoint of SU, so the first reason is given. Note, if we have a midpoint, we want to write down which segments are congruent. So our next step took ST congruent to TU. Notice I put the tick marks in the diagram, and the reason is the definition of midpoint. We knew that those two pieces were equal because T was the midpoint. So step 1 led us to step 2. Then it changes it to an equal statement. The reason why we change it to equal is I cannot substitute things in for congruence. It has to be with an equal sign, okay? So, ST is equal to TU. Yes, definition of congruent segments. Why that? If they're congruent, they have to be equal. We changed from congruent to equal in the world of segments. If you were working with congruent angles and you change from equal to congruence, it's going to be the definition of congruent angles. And then from there, the statement changes to a 7x equals 3x plus 20. Well, what's 7x? 7x is ST, so that gets substituted in. 3x plus 20 is TU, that gets substituted in. So we use the substitution property of equality, okay? And then from there it says that we're going to use the subtraction property of equality because we're going to solve the equation. So I'm going to subtract 3x from both sides and get 4x equals 20. And then finally, to finish, we would use the division property of equality to finish solving the equation. And we end with x equals 5, just like we were supposed to. So, last couple things here that we got to take a look at are the properties for congruent segments and congruent angles. And really, these should go pretty quick. We talked about this in the last video. Reflexive property, any segment is congruent to itself. As they were also equal to themselves, they can also be congruent. The only difference is if we use a congruent sign, we call it a POC instead of a POE. Same thing with the angles. If it's a congruent sign, we use the property of congruence. Property of congruence. If it's an equal sign, it's the property of equality. Symmetric property states that we can switch the order. If AB is congruent to CD, then we can flip it and say CD is congruent to AB. And finally, transitive. Notice again, both segments are congruent to CD. Therefore, they are congruent to each other. Transitive property. Three things that are all congruent. And the same properties fly with angles. Any angle is congruent to itself. We can switch the order of two. If A is congruent to B, then angle B is congruent to angle A. Flip it around. And finally, the transitive property, three things that are all congruent. Notice the B matches angle B. It's the same. So if A is congruent to B and B is congruent to C, then A also has to be congruent to C. So we will use those properties with a congruent sign and an equal sign. If we use it with a congruence, it's a POC. With an angle, it's a POE. So this one here, name the property that is illustrating it. So it says T is congruent to V and V is congruent to R. V's match. Therefore, T is congruent to R. That is the transitive property of congruence, POC. Okay? Make sure you look at the sign. This was a congruent sign, not an equal sign. And this one changes the order. JL is congruent to YZ. Then YZ is congruent to JL. Okay, it was the if then. So, that is the symmetric property of congruence because it is a congruent sign. Last proof. This video is getting a little bit long, so I'm going to pick up the pace a little bit through this one. So, on this one, we are going to prove that AB is equal to 2AM, so that's this statement here, and we're going to end with the 1/2 right here. So, how do we get there? Part 1 says M is the midpoint of AB. If that's the case, I want to mark it in the diagram, put the tick marks up. That is given. Given piece of info. Step 2 says AM is congruent to MB. Well, I took my midpoint and I made my congruent segments for step 2. Therefore, we use the definition of a midpoint. We took the given and used it. Step 3 says AM is equal to MB. This statement just changes from congruent to equal. They are segments. We use the definition of congruent segments. If they are congruent, they are equal. Now, whole different aspect here. AM, we brought AB into the game. Brought AB in. The reason why we brought AB in is because we have to prove something with AB. So AB is equal to AM plus MB. Segment addition postulate for step 4. We took the two parts of it and added up to be the whole thing. So I'm going to highlight that out. AM is here. One part. MB right here. Added the two parts to get the whole thing. And the reason why we knew we had to do that was because we have to end with AB. We hadn't had AB involved yet. AB had to get involved. Had to put them in there. Okay? Next step. Our MB changes to an AM. Well, AM is equal to MB from step 3, so I can use the substitution property of equality. I abbreviated substitution. And now step 6, this one's kind of tricky. I kind of like calling this combined like terms. It's also referred to as the distributive property. The book's probably going to go with distributive. And then finally, for step 7, we added these two together. They combine. The 2 vanishes. To get the 2 to vanish, and it'd be called a 1/2, I would say both sides were multiplied by 1/2. Or you could also say that it was divided by 2. So really, I would take either the division property of equality or the multiplication property of equality here. But multiplication is probably the best term because it's written as a multiplication. So multiplication property of equality, 1/2 times 1/2 cancels it out. So we've proven both statements. We are done. Have a great rest of the day. We'll keep working on these proofs.